Okay. So I'm going to do revision on entropy. So I revised second law of thermodynamics. The one more chapter in module 3 is entropy. It's one of the important chapter. So in entropy, first I'm giving the syllabus. What are the things you are learning in entropy? You are learning Clausius inequality, statement of Clausius inequality, entropy definition. To prove entropy is a property of system, change in entropy, entropy as a quantitative test for irreversibility, principle of increase of entropy, and entropy as a coordinate. These are uh, the contents of the syllabus. Okay. So first, you should know the entropy. The already we know the first law of thermodynamics gives rise to a new definition called as the internal energy. Like that, second law of thermodynamics gives rise to a new definition called as the entropy. Like other thermodynamic properties, pressure, volume, temperature, etc. Entropy is also a thermodynamic property of a working substance. Okay, and it is a valuable tool in second law analysis of engineering device. Okay, and entropy is a function of a quantity of heat which shows the possibility of conversion of that into work. Okay, the second law of thermodynamics mainly deals with the direction of flow of heat transfer. As we studied, according to the Clausius statement, the heat never flow from a lower temperature gradient to higher temperature gradient. Suppose if you assist with some amount of the work, then only the possibility of heat transfer takes place. Okay. And entropy formula is given by dq by T. Hence, it is a function of quantity of heat, which shows the possibility of conversion of that into work. The definition of entropy. Okay, it is just thermodynamic property and it is given by the formula dq by T. So as you add the heat to the system, entropy of the system increases. As you remove the heat from the system, the entropy of the system decreases. So already we studied the sign convention for heat transfer. So as you add the heat into the system, the energy increases. As you remove the heat from the system, the energy of the system decreases. Like since the entropy is directly proportional to or directly related to the heat, hence as you add the heat to the system, entropy of the system increases. As you remove the heat from the system, the entropy of the system decreases. Okay, so we can say that entropy is a function of quantity of heat which shows the possibility of conversion of that into work. Okay, so that is the concept related to the entropy. And now you see how you are going to represent in TS diagram. Okay, so we studied PV diagram like that. We are having TS diagram also related to the heat transfer. So T is Y coordinate and S is the X coordinate. Okay, consider the heating of working substance by a reversible process. We know that reversible process and irreversible process. The reversible process is one in which all the states are in equilibrium condition and it is a very slow process. We can stop the reversible process at any instant time and we can take back from that instant to the initial position. Hence there are no traces left out in case of reversible process. On the other hand, irreversible process is a very fast process. We are going to take from the initial state 1 and to the state 2, and it is very fast process and it is represented by the dotted line. Okay, and we cannot stop the irreversible process in between. We can stop the irreversible process only at the end state. Suppose you start the process at point 1, and we can stop only at the end state. That is the difference between reversible process and irreversible process. Okay, in engineering application we are going to deal mainly with the reversible process only. Okay, so because all the states are in equilibrium condition. So you consider this diagram, okay, TS diagram. Consider the heating of working substance by reversible process. Let dq is the amount of heat supplied to the working substance, which will increase the entropy by ds. Okay, as I said, as you add the heat to the system, the entropy of the system will increase. Okay, dq is the quantity of heat supplied to the working substance, and the increase in the entropy will be given by ds. Okay, according to our definition, dq is ds is dq by t. So based upon that equation, we can write dq equals to t into ds. You remember this is a formula, general formula for the entropy, but we are having the different formula for different process. According to the type of process we are having, we are getting the different formula, but general formula is dq equals to t into ds, where t is absolute temperature and ds is the increase in entropy. Okay, now let us consider one small elemental area dA. Okay, so in between process 1 to 2, okay, this is the entire process. As I said, the heat transfer is a path function, work transfer is also path function. On the other hand, all the thermodynamic properties like pressure, volume, temperature, all are point functions. Okay, the point functions are having the definite values at that particular state points. For example, P1, V1, T1, P2, V2, T2 means all these thermodynamic properties have the definite values at the particular state point. On the other hand, the work done and heat transfer are the path functions. Okay, they do not depend upon the end state, rather they depends upon the entire path followed during the process from 1 to 2. Okay, and we are going to represent P1, V1, and T1 like that. We are not going to represent like W1, Q1. We are not going to represent, but we are going to represent work transfer and heat transfer as Q1 to 2 and W1 to 2, etc. Okay, because these two are path functions. So the total heat supplied or absorbed is given by the integration of dq between the limits 1 to 2, between the state points 1 to 2 equals to the integration of tds. Okay, general formula is dq into td, dq equals to tds. So that is we are going to consider at a particular point in order to obtain the entire heat transfer from point 1 to point 2, we are going to integrate this equation between the limits 1 to 2. So that is integration of dq between the limits 1 to 2 equals to integration of tds between the limits 1 to 2. And also the change in entropy is given by ds equals to dq by t. Or we can write integration of ds between the limits 1 to 2 equals to integration of dq by t between the limits 1 to 2. Okay, so because entropy is a property, so we can write it as S2 minus S1. Okay, you remember pressure, volume, and temperature, these are thermodynamic properties like internal energy, enthalpy, and entropy are also the thermodynamic properties, and they are all point functions. And you remember cyclic integral of any property is equals to 0. That is cyclic integral of dv is equals to 0, cyclic integral of dt equals to 0, cyclic integral of dp equals to 0, cyclic integral of any thermodynamic property is 0. Okay, so internal energy and entropy are also the thermodynamic properties, and they are point functions. Okay, so integration of ds equals to the integration of dq by t. So we can write s2 minus s1 equals to the integration of dq by t. Or in general, we can write ds equals to dq by t. Remember, this is the formula for entropy. So entropy is property of the system and is mainly related to the heat transfer. As you add the heat to the system, the entropy of system will increase. As you remove the heat from the system, the entropy of the system will increase. So it's all about entropy. Next, we are going to learn Clausius theorem. Okay, here in this chapter, mainly we are going to study Clausius theorem, Clausius inequality, then irreversibility, the entropy change during various processes like constant volume process, constant pressure process, isothermal process, adiabatic process, polytropic process, etc. The first important thing in this chapter is Clausius theorem. Okay, Clausius theorem. So before understanding Clausius theorem, you have to understand this diagram. Okay. So first, you have to draw the PV diagram. So first, you have to draw a smooth closed curve. Okay, the whatever the structure is there, this is the original reversible cycle. So just you draw one a circle diagram. Okay, like this. Okay, and then you have to cut this original reversible circle by means of number of reversible adiabatic lines. Okay, first you draw this original reversible cycle and then cut this original reversible cycle by means of number of reversible adiabatics. So okay, see what curves you are seeing on the screen. These are all reversible adiabatic lines. Okay, these are 1, 2, 3, 4 like that. You have to cut the original curve into the number of reversible adiabatic line. We know that the adiabatic process is the one which follows the law PV raised to gamma equals to constant, where gamma equals to ratio of specific heats Cp divided by Cv, and gamma is 1.4 for air. Okay, and the value of gamma varies according to the type of gases used. Okay, and so first original reversible cycle, then it is cut by the number of reversible adiabatic lines, and then we are going to cut at the top and bottom. You see, this is the one line, this is isothermal line. So at the top and then at the bottom, so we are having the one more line like that. We are going to cut at the top and bottom by number of reversible isothermal lines. Okay, first original cycle, then we are having the reversible adiabatic lines, and then we are having the reversible isothermal lines. Okay, here in this case you take one of the cycle A, B, C, D like that. You can name E, F, G, H like that. You can name that is A, B. CD is the one such cycle which is having the four process. AB is our reversible isothermal process in which the dq1 is the heat added reversibly at constant temperature process. Next, BC is the reversible adiabatic expansion, and then CD is the reversible isothermal compression. Okay, where the heat is rejected by an amount of dq2. Okay, so we studied a Carnot cycle in the previous class. Carnot cycle is the one which is having the two reversible adiabatic process and two reversible isothermal lines. Okay, first one is AB isothermal expansion, in which the heat is added at constant temperature. Then process BC is our reversible adiabatic process. Okay, reversible expansion process. And then CD is our reversible isothermal compression process, and DA is the reversible adiabatic compression process. Like that we are having. So whenever you divide the original cycle into the number of Carnot cycles. Okay, so all the cycles represents Carnot cycle. As I said, Carnot cycle is practically not possible in nature because it is very difficult to achieve the isothermal process very slowly, and it is very difficult to achieve the adiabatic process at the faster rate. So we cannot stop the engine in between. So whenever you start the engine, we are going to stop only after following all the process. Hence, the Carnot cycle is practically not possible. It is impossible, but it is used as a reference for other cycle. Okay, in basic thermodynamics you are learning only the Carnot cycle. but in applied thermodynamics, we are having the gas power cycles, power cycles, like we are having a auto cycle, diesel cycle, then dual cycle, auto cycle, diesel cycle, dual cycle. We are having auto cycle, diesel cycle, and dual cycle in gas power cycles. Okay, and we are having the vapor power cycle. In vapor power cycle, we are learning the Rankine cycle and Carnot cycle once again in vapor power cycle, and in gas turbine cycle we are studying Breton cycle, reversed Breton cycle. Okay, and in refrigeration also we are having the cycles. Okay, so your applied thermodynamics is fully of the cycles, but in basic thermodynamics we are learning mainly the Carnot cycle. Okay, so whenever you divide the original reversible cycle into the number of reversible isothermals and reversible adiabatic process, so the each cycle represents a Carnot cycle. In Carnot cycle, we are having two process, two reversible isothermal process, and dq1 is the heat added to cycle at constant temperature. dq2 is the heat rejected from the cycle. Like that, you consider another cycle like the EFGH is the another cycle in which dq3 is the heat added reversibly at isothermal process, and dq4 is the heat rejected from the cycle at constant temperature. Like that, we are having the number of Carnot cycles. Okay, now we are going to write the equation as Q1 is proportional to T1 and Q2 is proportional to T2. Because the heat is directly related to temperature, we can write Q1 equals Q1 by Q2 equals to T1 by T2, or we can write Q1 by T1 equals to Q2 by T2. Okay. Okay, whenever the cycle is working between the source and sink temperature, already we studied the source and sink in second law of thermodynamics. Okay, source is the one which is having the highest temperature. The heat engine which receives the heat from source and reject the heat to the sink. Source temperature is always higher than the sink temperature. Then only the heat transfer takes place. Okay, so whenever the engine working between two thermal reservoir, one is source and one is the sink, then Q1 equals Q1 by Q2 equals to T1 by T2, or we can write Q1 divided by T1 equals to Q2 divided by T2. Okay, so according to the sign convention, the heat added is taken as positive and the heat rejected is taken as negative. So we can take the negative magnitude in RHS. The Q1 divided by T1 equals to minus Q2 divided by T2. So whenever you shift the RHS term towards left hand side, we can write Q1 by T1 plus Q2 divided by T2. This is for one cycle, one Carnot cycle. But so here you see we are having the number of Carnot cycle. So we can write Q1 divided by T1 plus Q2 divided by T2 plus Q3 by T3 plus Q4 by T4, like that. The number of cycles we are having up to n number of the cycles. Okay, so this is for one cycle. Q1 by T1 plus Q2 by T2 equals to 0 for first cycle. Like that, Q3 by T3 plus Q4 by T4 equals to 0 for second cycle. Q5 by T5 plus Q6 by T6 equals to 0 for third cycle. Like that, we can take n number of the cycle. Okay, so we can write it as summation of Q by T equals to 0. And one more thing, here we have to represent R. The letter R indicates the reversible process. So all the processes are reversible in nature. So summation of dq by t is equals to 0 for reversible process. Mathematically, we can write cyclic integral of dq by t equals to 0. So for reversible process, okay, how we are having cyclic integral of dv equals to 0, cyclic integral of dt equals to 0, like that. Cyclic integral of dq by t equals to 0. So this is known as the Clausius theorem. Clausius theorem tells that summation of Q by T for reversible process is exactly 0. So whenever we ask the state and prove Clausius theorem, first you have to draw this diagram, that is Clausius theorem, cyclic integral of dq by t equals to 0. The same formula we are going to use in the numericals. Okay, next we are having one more important thing, as I said, the Clausius inequality. Okay, so the most important concept in entropy chapter is Clausius inequality. So this question may ask for 10 marks. So here diagram is important. Once again, the diagram is important. We have to take the temperature, this is the x y coordinate, and this is the volume in the x coordinate. So first we have to draw this one curve AB. AB is a general process. It may be reversible or irreversible process. Okay. We came across this type of concept in Carnot's theorem. Okay. Carnot's theorem states that of all the engines, the reversible cycle is the one which gives the maximum efficiency. Here AB is any general process. It may be a reversible process or it may be irreversible process. Once again, we have to cut the number of reversible adiabatic lines. Okay, so first AB is any general process, then after that we are going to cut this process by number of reversible adiabatics, and then we are having one more. This is a horizontal straight line. So this is a constant temperature process. So these three lines we have to draw. First AB general process, and these are the reversible adiabatic lines, and then finally we are having the constant temperature line. Now A, B, C, D is a cycle in which the process AB is any general process. It may be reversible or irreversible. The process BC is the reversible adiabatic expansion process. The process CD is the isothermal process or constant temperature process, and process DA is the reversible adiabatic compression. So we have to divide this cycle like this. So process are most important here. You have to mention everything. And here at the top, at the bottom, we are having only one isothermal process, but at the top we are having the number of isothermal lines. Okay, divide this process into the number of isothermal lines. Okay, and T equals to constant. T equals to constant means isothermal process. And here you take one of the cycle. Once again, all the cycles are of Carnot cycle type, where we are having the two reversible isothermal lines and two reversible adiabatic lines. You consider one of the Carnot cycle in which dq is the heat added to the cycle reversibly at constant temperature, and dq2 is the heat rejected from the cycle at constant temperature. Okay, we consider one of the cycle. Now we know that the efficiency of any cycle is given by the amount of heat supplied minus amount of heat rejected divided by amount of heat supplied. That is Q1 minus Q2 divided by Q1. Okay. But here we consider dq as the heat added to the system, and dq2 is the heat rejected from the system. Okay, so and we know that the efficiency of a general cycle is always less than the efficiency of a reversible cycle according to the Carnot theorem. So Carnot theorem states, suppose you take the number of engines, among all the engines, reversible engine is the one which gives the maximum efficiency. Okay, based upon that one, we can write the statement as the efficiency of a general cycle, it may be reversible or it may be irreversible, is always less than the efficiency of a reversible cycle. So mathematically we can write eta is less than or equals to the eta reversible. Okay, so efficiency of general cycle is less than or it may be equals to eta reversible. Now we are writing the expression for the efficiency of general cycle as 1 minus dq2 divided by dq is less than or equals to 1 minus dq2 divided by dq reversible. So don't show reversible in the LHS term because it is a general cycle. But the right hand side we are having the reversible cycle. We can write it as 1 minus dq2 divided by dq is less than or equals to 1 minus dq2 divided by dq reversible. Okay. Now I am neglecting the one on both sides. Okay, neglecting the term one on both sides. We can write minus dq2 divided by dq is less than or equals to minus dq2 divided by dq for reversible engine. Okay, the first you write the expression for efficiency, then write the equation for efficiency. Okay, next neglecting one on both sides of the equation, we can write minus dq2 divided by dq is less than or equals to minus dq2 divided by dq is reversible. Okay, so now, okay, so now I'm going to remove the minus on both sides. This is the most important step. Okay, whenever you are going to remove the minus on both sides, okay, suppose if you are going to express in positive magnitude, in that case this sign vary. Okay, instead of writing less than or equals to, you can change it to greater than or equals to. This step is most important. So here don't write less than or equals to whenever you are changing the magnitude. Okay. So dq2 divided by dq is greater than or equals to dq2 divided by dq reversible. Next, what I'm going to do, okay, so now I'm changing the terms. Okay, these three steps are most important in Clausius inequality. Whenever you are changing the magnitude, so we have to change the greater from lesser than to greater than symbol. That is dq2 divided by dq is greater than or equals to dq2 divided by dq reversible. Okay, now what I'm going to do, I'm taking dq2 as the denominator of dq. Okay, so now you see I'm changing the things. Instead of taking in the denominator, I'm taking in the numerator. Okay, for example, you take one example, 3 is greater than 2. Okay, now 1 by 3 is less than 1 by 2. Like that, you take one numerical example and you can write. Okay, so if you're not understanding this term, you take one number. So here I am taking 3 is greater than 2. Okay, but whenever you take the reciprocal, that is 1 by 3 is less than 1 by 2. It is not greater than 1 by 2. So like that, if we take the example, so now I am changing the denominator term into numerator term. Okay, I'm taking dq as the numerator and dq2 as the denominator. Here also dq as the numerator and dq2 as the denominator. So dq by dq2 is less than or equals to dq divided by dq2 reversible. But we know that whenever you consider a reversible cycle, so dq divided by dq2 reversible is always equals to the temperature T divided by temperature T2. We consider T and T2 here in this cycle. You see, T is the temperature supplied, that is amount of the heat supplied during isothermal process at temperature T, and dq2 is the amount of the heat rejected by the cycle during temperature T2. Okay, we consider temperature T and T2. For that purpose, we are going to write the expression for dq divided by dq2 reversible cycle is T divided by T2. Remember, the heat transfer is directly proportional to the temperature, and dq2 is the heat rejected is directly proportional to the temperature T2. Okay, now substituting the value of dq divided by dq2 reversible equals to T divided by T2 in above equation. Okay, that is dq divided by dq2 is less than or equals to T divided by T2. Okay, so dq divided by dq2 is less than or equals to T divided by T2. In the next step, what I am going to do, just I am interchanging the term. Okay, I am taking the T as the denominator of dq and dq2 as the numerator of T2. Okay, so here first you have to replace dq by dq2 as T divided by T2, and in the next step I am taking the T as the denominator of dq and dq2 as the numerator of T2. So dq divided by dq2 is less than or equals to T by T2, or dq by T is less than or equals to dq2 divided by T2. And you remember, this is for any general process AB. Okay, so less than or equals to dq by T is less than or equals to dq2 divided by T2 for any process AB. But for reversible process, we know that ds is exactly equals to dq by T, or it is equals to dq2 divided by T2. Okay, so for any reversible process, for irreversible process, we can write dq by T is less than or equals to dq by T2, and but for uh, reversible process, it is exactly equals to dq by T, or it is equals to dq2 divided by T2. Okay, so we can write dq by T is less than or equal to dq2 divided by T2. Okay, according to the entropy formula, we can replace dq by T as ds. Okay, so you see, so whatever equation we are having, dq by T is less than or equals to dq2 divided by T2, we can replace the right hand side term with ds. That is, dq by T is less than or equals to ds for any process AB. Okay, suppose if you take the cyclic process, just you have to add the cyclic integral on both sides. Okay, that is cyclic integral of dq by T is less than or equal to cyclic integral of ds for cyclic process. Okay, now first you write dq2 divided by T2, and then we are going to replace this term by ds, because ds equals to dq2 divided by T2. So cyclic integral of you. So whenever you are going to represent for cyclic, we are going to represent it as cyclic integral of dq by T is less than or equals to cyclic integral of ds for cyclic process. But we know that ds is 0 for cyclic process, because the entropy is a property. ds equals to 0 for a cyclic process, because entropy is a property of system. So cyclic integral of dq by T is always less than or equals to 0. Okay. This is called as the Clausius inequality. Okay, so Clausius theorem is different. S equals to 0 for a cyclic process. Cyclic integral of dq by T is less than or equals to 0. Okay. Cyclic integral of dq by T is less than or equals to 0. This is called as Clausius inequality. So it is called as Clausius inequality. Whenever they ask to prove the Clausius inequality, so you have to prove first. You have to draw this diagram, and then you have to prove up to this point. Cyclic integral of dq by d is less than or equals to 0. Hence, we can sometimes they may ask check the reversibility of a cycle by Clausius inequality. That is the most important step, last step. That is, if cyclic integral of dq by t is less than 0, then it is called as the process is possible and irreversible in nature. If cyclic integral of dq by t is equals to 0, then it is called as the process is possible and reversible in nature. If cyclic integral of dq by t is greater than 0, then the process is not possible at all. So these are the three criteria we are getting in Clausius inequality. Okay, so don't stop here. You have to add three more steps by adding the three steps to this Clausius inequality. So cyclic integral of dq by t is less than 0 for reversible process. Cyclic integral of dq by t equals to 0 for a reversible process, and cyclic integral of dq by t is equals to greater than 0 for Venkatesh class ನಡೀತಾ ಇದೆ. The next concept, we have to prove the entropy is property of the system. As I said, like other properties, entropy is also the property of the system. For that purpose, so we have to draw the diagram. 1 to 2, okay. So here you see we are having the three paths. Okay, so 1 to 2 by following path A. So 1 to 2 by following path B, and 2 to 1 by following path C. Consider starting from point 1, proceeding on path A to 2. Okay. So you see, first you draw the diagram. But here in this diagram, we are having the two paths we are taking from 1 to 2, A and B, and from 2 to 1 by following the path C. Okay. So according to Clausius theorem, we know that cyclic integral of dq by t equals to 0. So for that purpose, we are going to write the equation as integration of dq by t between the limits 1 to 2 for the path A, plus integration of dq by 2 for the path 2 to 1 for the path B equals to 0. Okay. Because we are considering a cyclic process, first we are taking the A and B, that is summation of dq by t is 0 according to the Clausius theorem. First we are taking the two paths, that is first 1 to 2 by A, and then 2 to 1 by following path B. Okay. So integration of dq by t for the path E, that is we have to write the path also, that is 1 to 2, plus integration of dq by t for the path 2 to 1 for the path B equals to 0. Now I am considering 1 to 2 by following path A and returning from 2 to 1 by following path C. That is executes a cyclic process. So we can write the integration of dq by t for following path A between the limits 1 to 2, plus integration of dq by t between the path 2 to 1 by following the path c equals to 0. Or from the two equation, so when you compare the equations 1 and 2, so it is clear that the cyclic integral of dq by t between the path 2 to 1 by following the path b is exactly equals to 0, exactly equals to the integration of dq by t between 2 to 1 by following the path c. So you have to come first, you have to write the Clausius theorem for one cycle considering A and B, and in the next step you have to write the Clausius theorem for the two process A and C. Okay, so by comparing the two equation, we can write that is integration of dq by t between the uh, path 2 to 1 by following path p is exactly equals to the integration of dq by t between the state points 1 to 2 to 1 by following the path c. Okay, so by this one, hello, hello, hello. So by these two equation, it is clear that uh, entropy is independent of the path followed. Okay, so while so either you take the path B or path C, so the magnitude remains same. Okay, that is integration of dq by t for the path B is exactly equals to the integration of dq by t for the path C. Hence, we can say that the thermodynamic entropy is a property of the system, and it is always independent of the path followed. So, hence, it is a property of the system and also the point function. Whenever it is a property of the system, obviously, it is a point function. Okay. So like that, we're having one more concept called as internal energy. So in first law of thermodynamics, they used to ask, prove that internal energy is a property of the system. Like that, in entropy also, we are having a concept called as the entropy is the independent of the path followed, but it depends upon the state point. Hence, whenever it depends upon the state points, we can tell that the entropy is the independent of the system and it is a property of the system. So entropy is a property of the system. Okay, and it is independent of the system. Okay, so we are having a concept called as third law of thermodynamics. Okay, the third law of thermodynamics was formulated by German chemist and physicist Walter Nernst. Okay, according to the third law of thermodynamics, the entropy of a perfect crystal or perfect substance is zero when the temperature of the substance is exactly equals to absolute zero. Second law of thermodynamics related to the direction of heat transfer. The first law of thermodynamics related to the energy transfer, that is law of conservation of energy. Zeroth law of thermodynamics deals with the concept of temperature and concept of thermal equilibrium, whereas the third law of thermodynamics is mainly related to the entropy. That is, entropy of a perfect substance is zero when the temperature of the crystal is exactly equals to the absolute zero. These are the important concepts we are going to learn in entropy. And so I'll solve one simple problem related to entropy. So this is a problem. Air in a closed vessel of fixed volume 0.15 meter cube exert a pressure of 12 bar to at 250 degrees Celsius. If the vessel is cooled so that the pressure falls to 3.5 bar, then determine the final pressure, heat transfer, and change in entropy. So here V1 is 0.15 meter cube, P1 is 12 bar, and P2 is 3.5 bar. T1 is 250 degrees Celsius, 273 plus 250, that is 523 Kelvin. We have to calculate the final pressure, heat transfer, and change in entropy. So first, we have to find out the mass of the gas, apply the ideal gas equation. P1 V1 equals to MRT1. So mass of the gas is given by P1 V1 divided by RT1. Okay, so P1 is 1200 kilopascal into V1 is 0.15. Next R, the general gas constant is 0.287 into T1 is 523. That is 273 plus 250 Kelvin. That is 523 Kelvin. This after solving, we are getting the mass of the gas as 1.2 kg. And to find out the final pressure, once again apply the P1 by T1 equals to P2 by T2. So from that one, we are obtaining the T2 as a T1 into P2 by T1. So you remember all the values you are going to express in terms of Kelvin. Okay, so don't put it in degree Celsius. 523 into 3.5 divided by 12, we are getting 152.54 Kelvin. Okay. Next, heat transfer. Heat transfer is given by, you'll see, heat transfer Q equals to mCp into dt. Okay, so use this formula 1.2 into 1.005. T2 final temperature is 152.54 minus 52.3. And one more thing, change in entropy. I have derived the change in entropy for all the process like constant volume. We are getting mCV into ln T2 by T1. For constant pressure process, we are getting mCp into ln T2 by T1. And for constant temperature, all the uh, process I have derived. Okay, so you have to use the general equation which gives the entropy change in terms of pressure and temperature, because we are having P1 and P2 and T1 and T2. So identify the equation which is related to the final temperature and initial temperature, the final pressure and initial pressure. So M is 1.2 into 1.005 ln, that is natural logarithm. Don't take log to the base 10, you have to take natural logarithm. T2 is 152.54, 523 minus of 0.287 into ln of 3.5 divided by 12. So after doing this one, we are getting the change in entropy as minus 1.06. You'll see negative sign indicates that there will be a decrease in the entropy of the system, and positive sign indicates the increase in the entropy of the system. So I'll stop the session now. Those who have not entered USN, please enter in the chat box. Any doubts in entropy chapter, guys? Not only in entropy chapter, in any chapter. If you are having any queries or doubts, you can ask. one of the important chapter in basic thermodynamics, entropy chapter. Try to understand the concepts properly. So those who have missed out your entry in the chat box, please enter as early as possible.